So here we have a diagram of a physical system where we're going to show how, when you're pushing on a spanner in different ways, how you can actually draw that diagrammatically and with an oblique force work out the components to work out a moment, and show a different couple of ways of working out the moment. Now remember that we said the moment is the twisting. A moment is always worked out by the force, we're pressing down, times its perpendicular distance, and we write that here, moment is force times perpendicular distance. So whichever direction the force is in, the moment arm always has to be perpendicular to the force. So if we had a nice simple straight down force like this, we could work out our moment as that force times that perpendicular distance. You intuitively know this because when you use a spanner, you usually, it doesn't matter which angle you put it at, you always press perpendicular down to the spanner. If you're up here, you're still pressing this way, perpendicular. And if you're down here, you press this way, perpendicular. If you press along the line of the moment arm, nothing happens as far as twisting goes. That is, there is no moment. You can see, because your force is along this line, there is no perpendicular distance. So it's a force times 0, which is nothing. Now if you press obliquely, which often happens for some reason or another, you can't press straight down, what happens then? How do we work out the moment then? Well, we can draw it here on the diagram. If we have a force coming this way, okay, we can see that that force actually has a line of action going through there. It's your line of action down through here. And the line of action always has a horizontal and a vertical component. And we can use those components because the vertical component is always perpendicular to the moment arm. So we can see, to work out those components, what we do is we make the line of action of the force the diagonal of a parallelogram. And we can see there's the horizontal component and there's the vertical component of that force. Now often we're given this angle here, okay, which is the same as this little angle in here, which is the same as this angle here. And we can now use trigonometry to work out what this vertical component is in order to work out the moment. So we now no longer worry about this one for the moment. The moment is now, we're working out the moment due to this vertical component. And this vertical component here is F sine theta. Okay, so now we know that the moment due to this vertical component here is equal to F sine theta times its moment arm, which is that same distance along there, d, call it distance d. Okay, and what's the moment due to the horizontal component? Well, it's nothing, because as we said before, if you press along there, nothing happens, there's no moment. Okay, and we can see that because the moment is the force times the perpendicular distance, and that's 0. So the moment along here is 0. There's no twisting. So that's the moment, how to find a moment from an oblique force. You need to use the oblique force as the diagonal to work out the vertical and horizontal components at the point where the force is touching the moment arm. Now, sometimes you actually want to work it out in a different way. You don't actually want to work it out finding the components, because as this force is coming down here, we can see that instead of working out the components here, what we can do is work out the perpendicular distance from the force back to the bolt, which is where the moment is acting around. So if we can work out that perpendicular distance there, we can multiply the force times the perpendicular distance, which is now the new moment arm. And as you can see, this distance here is actually going to be shorter than the spanner itself, because this is getting closer in. Okay, so how do we work that out? Well, we can do it this way. So we can take the force through its line of action all the way here through to the place where it has a perpendicular moment arm. Okay, so we know the force, and this time we have to calculate this distance here. Well, if we know that this angle here is theta, you can see we've got a right angled triangle here. Once again, what we have here is d sine theta for that length. So once again, the moment here is now the original force times the perpendicular distance back to the point, which is d sine theta. So the moment is f d sine theta. So you can see, working out the moment this way, you get the same value. So you can see that working out the value this way, using the force times the perpendicular distance back to the point, is the same. You get the same value as if you worked it out this way, where you took the vertical component of the force and then multiplied that by its moment arm, or perpendicular distance, back to the point. Because here you used f sine theta times d, and here you use d sine theta times, here you use d sine theta times f. So that's to show that you can work it out the moment neither way, using the principle that to work out a moment you always have to have a perpendicular arm to the force. So perpendicular moment arm to that force, or a perpendicular moment arm to that force, and you'll get the same strength. Now, remember that moments also have a sign. So here, when we're pushing down the spanner this way in the nut, we're pressing counterclockwise. And we know that when we're pressing counterclockwise, in order to achieve a goal of loosening something, which is where the effort is required, that's the positive direction. That counterclockwise twisting is positive. Spanner will twist around that way, the bolt will twist around that way, and that's positive. If we were tightening the bolt, then we're creating a moment in the negative direction. Positive when we're loosening.